Hey everyone, this is Dr. Walker. This is video 569, torque on a current loop. I'd like to start this video with a question. An electric toothbrush or electric drill, you turn it on and then something starts to rotate. So what do you think is in that toothbrush that allows it to rotate? Please put your thoughts in the comments below. What I'd like to discuss in this video is torque on a current loop. We just learned that if you have a wire that carries a current and it's in an external magnetic field, that it will experience a force. So now let's consider a current loop. You can just think of it as 4 wires that are carrying current and it's in an external field. So each segment of the wire will experience a force. If the loop is oriented in a certain way, then the loop will start to rotate. So it's easier to see that by looking at a loop when the plane of the loop is parallel to the magnetic field. It's a little bit easier to see how this magnetic field and the current is going to allow this loop to rotate. So let's consider the force on each individual wire part of the loop one at a time. So segment 1 over here. The current is to the left and the magnetic field is to the right. And we know that we have the expression F equals IL cross B to find the force on a segment of wire. So when I and B are parallel or anti-parallel, we know that the cross product is 0. So there's no force on segment 1 or on segment 3 either. What about segment 2? Well, the current and the field are perpendicular, so we can use our right-hand rule number 1 to figure out the direction of the force. You should point your fingers downwards in the same direction as the current, and your palm should be facing to the right so that you can fold your fingers to the right. So go ahead and do that with me. And you should see that your thumb is pointing towards you, which is out of the page. If you do the same thing for segment 4, since the current is going in the opposite direction, it means that the force, your thumb, will point into the page. All right, so go ahead and try that. But what's going to happen is that this loop will rotate. You can imagine this loop being on a table. And if you push down, and here if you pull up, it's going to rotate. So it's kind of hard to visualize. So in this second picture here, we have a side view of the loop as viewed from side 3. Since we said that the force was coming out of the page, if we're now looking from the viewpoint of side 3, that force out of the page is upward. Imagine your table like this, right? And the force into the page here, into the table, is now downwards. So when we view it from this angle, it's easier to see that the loop is rotating clockwise. So if the loop is oriented a certain way with respect to the magnetic field, it will rotate. Let's go ahead and figure out an expression for the torque. Remember from physics 1 that when we have a force at a certain distance from a pivot point, then your object will rotate. Using the definition F equals IL cross B, and knowing that when the current and the magnetic field are perpendicular, that this equation becomes ILB to find the magnitude of the force. It's just ILB. So that's what F2 is going to be, and F4 is going to be ILB. But this wire here that experienced a force, it was segment 2 and segment 4. What is the length of that wire? It's not L, the length is A. So we're going to say the force on number 2 is equal to the force on number 4. I'm just looking at the magnitude, and it's going to be IAB since the length of those two segments are A. And now let's look at torque. May have been a while since you've calculated torque, but the easiest way to calculate it if the force is perpendicular to the object being rotated, then you just multiply the component of the force that's perpendicular, which is the whole force, times the distance from that force to the pivot point. Usually we call this R. And so it's R times F perpendicular, but F is already perpendicular. So R is half the length of the shorter side B here. So R is equal to B over 2. So that means that the torque produced by F2 is going to be F2 B over 2, right? The force times the distance because they're perpendicular. And then if you look at the torque exerted here by this force number 4, it's going to be the same thing because the force has the same magnitude as F2 and is acting at the same distance from the pivot. And both forces are causing a clockwise rotation, so we can just add the two forces since the torques are in the same direction. So when this is F4 here, so now we just can put in the definition, IAB times B over 2 plus IAB, big B here, times B over 2. And so that's going to give us IABB, and we're almost done. A times B here is the length times the width of the loop. So length times width is area. So this is a special case. It was just a lot easier to visualize and calculate torque from this angle. But we can see that the torque on this loop, when the magnetic field is parallel to the plane of the loop, the torque is IAB. And this is going to be the maximum torque on the loop. We're going to see in the next slide, when we have an angle, we can still definitely calculate the torque, but it's going to be less. So this is an expression to find the magnitude of the maximum torque on a loop, which happens when the plane is parallel to the magnetic field. So now let's look at the more general case when there is an angle between the loop and the magnetic field. So imagine this is the same loop as before, and we're looking at the side view from side number 3 again. So the rest of the loop is going into the page. It's hard to draw that, right? This doesn't really look into the page, that's why it's not drawn. But if the loop is at an angle, we're still going to have side 2 experiencing a force upward and side 4 experiencing a force downward, just like if the loop was horizontal, which it was in the previous slide. All right, so that being said, how do we find the torque on this loop now? This is a more general case. Another way to find torque when the force is not perpendicular to the object being rotated is to find the magnitude of the torque is just the force times the moment arm. And the moment arm is the perpendicular distance from the pivot to the force. So what you do is you extend that force line straight, and then you find the shortest distance from the pivot to that force. That's called the moment arm. So that's labeled here with this horizontal dashed line, and the length of this moment arm is b over 2 sine theta, since the hypotenuse is b over 2, and this side is opposite of the angle theta. So the torque on this loop now, the magnitude of the torque is going to be F2 b over 2 sine theta, right, instead of just F2 b over 2. And then we're going to add up the torque due to F4 as well, plus F4 b over 2 sine theta. So when we do this, we're going to get IAB for the force, right, times b over 2 sine theta. And we can go ahead and we'll just go ahead and write it out. B over 2 sine theta plus IAB b over 2 sine theta. And now we can go ahead and combine all of these terms and simplify the A times the load B as the area like we did in the previous slide. And we're going to get IAB sine theta. So we do need an expression for the vector form since torque is a vector. So what we can do to write this as a vector and this to be our final form, we can define an area vector A whose magnitude is the area of the loop, which is the length times the width, but the direction of this area vector is going to be perpendicular to the plane of the loop, as you can see in this picture here. So if you had a loop like this, that area vector will be perpendicular to the plane of the loop. And then AB sine theta is the cross product of A and B. So now we have an expression for the torque on a current loop in a uniform magnetic field. We'll definitely do an example in the next slide, in the next video, and in the second part of this video we're going to see a really cool application which relates to the question that I asked at the beginning of this video. The last thing I want to say is this equation should look a little bit familiar. Back in video 512, we were talking about electric dipoles, and we found the torque on an electric dipole, and it was the electric dipole moment cross electric field. So an electric dipole in an electric field rotates, and a magnetic dipole in a magnetic field will also rotate. So that's a nice comparison to make, and I will see you in the next video.